All right, welcome. Today, we're diving deep into the engineering that powers our world. We're talking about the high-voltage heart of the electrical grid, the gas-insulated substation. We're going to go from the first digital sketch all the way to flipping the switch to see exactly how these incredible pieces of tech are built.
So, let's just start with the core problem, the big question. You've got 380,000 volts of raw power, enough to light up a city, but you're in the middle of that city where space is everything. How in the world do you handle that kind of energy safely? Well, the answer is a really clever piece of engineering called a gas-insulated substation, or GIS for short.
You know, a project of this scale doesn't start with a shovel. It starts right here, on a computer. Before anyone even thinks about breaking ground, every single piece, every wire, every safety clearance is mapped out and calculated down to the millimeter. This is where the digital blueprint is born.
So what exactly is a GIS? Honestly, the best way to think about it is a high-voltage substation in a can. All the parts that are buzzing with electricity are sealed inside these metal tubes, filled with a special gas called SF6. This gas is an incredible electrical insulator, which means you can shrink the whole setup down, making it compact enough to fit right into a packed urban landscape. It's a total game changer.
Now, the number one rule in high-voltage engineering is safety, and it all starts with clearance. That's just the mandatory empty space you need around anything with that much energy. And as you can see, the more voltage, the bigger that safety bubble has to be. At 380 kilovolts, we're talking a minimum of 3 meters. And trust me, these aren't suggestions. They are ironclad rules you do not break.
Okay, this is where the math gets really serious, because you have to plan for the absolute worst-case scenario. That top formula, that calculates the short-circuit current. It's basically the biggest electrical punch the system could ever possibly throw. And that one number, it dictates almost everything else. How thick the steel needs to be, what kind of bolts to use, all of it is designed to withstand that massive surge of power for a split second so the lights stay on for everyone else.
All right, so the digital plan is locked and loaded. Time to get our hands dirty and make this thing real. We're moving from the design phase to the construction site. This is where the heavy lifting of civil engineering provides the solid foundation for all that high-tech equipment to come.
Building something like this is like a carefully choreographed dance. First, you dig. Then you build the skeleton, a web of steel rebar, before you pour these incredibly strong concrete foundations. After that, you lay in what are basically underground highways for all the power and control cables. And last, but maybe most important for safety, you install this huge copper mesh in the ground. It's a giant safety net for electricity.
So, you're putting hundreds of tons of gear on this concrete slab. How do you know it won't just crack? Well, you don't guess. You use math. This formula tells engineers exactly how much steel rebar, that's the AS, they need to put inside the concrete. It's all about making sure that foundation can handle the immense weight and forces pushing down on it, not just for a year, but for decades.
Okay, the foundation is poured, the building is up. Now we get to the really cool part, the high-tech assembly of the GIS modules themselves. This is where we install the actual heart of the substation.
If you think about the substation as a body, these are the vital organs. The circuit breakers are the lightning-fast reflexes that stop problems. The busbars are the main arteries, carrying all the power. The isolators and grounding switches are like safety valves that let crews work on it safely. And the CTs and PTs, they're the nervous system, constantly sensing and measuring the flow of electricity. It's a beautiful system.
Now, this is absolutely crucial. That SF6 gas is the only thing keeping all that voltage contained, so you have to be 100% sure it never leaks. To do that, every single sealed compartment is put through a stress test. They pressurize it to 1.3 times what it'll ever experience in real life just to prove it's perfectly sealed. It's a simple formula, but it's a make-or-break quality check.
And you know, not all of these GIS halls are created equal. The design changes big time depending on the voltage. A 380 kilovolt room, that's the heavyweight champion. The components are massive, you need more space, you even need powerful cooling systems to handle the heat. Compare that to a 115 kV room, which is more like a middleweight. Still incredibly powerful, but much leaner and more compact.
So it's all built. The connections are torqued, the gas is filled, but you can't just flip the on switch. Not even close. Now we're at the final, most nerve-wracking stage. A whole series of tests to prove this thing is absolutely ready to join the grid. This is the final exam.
Look at this number, less than 5 picocoulombs. That is an unbelievably tiny amount of electrical charge. This is the passing score for what's called a partial discharge test, and it's basically a test for perfection. Any reading higher than this means there's a microscopic flaw somewhere. A tiny speck of dust, a minuscule imperfection that could grow into a massive failure years from now. They are literally listening for an electrical whisper.
So bringing the station to life is a super careful, step-by-step process. You run final checks on the insulation. You analyze the gas one last time to make sure it's pure. You test every single control and safety system, the whole SCADA network, to make sure the brain is talking to the body. Only when every single box is checked do they finally give the command to energize.
And when you look back at the whole thing, you see it all comes down to the language of engineering, which is math. There's a formula for the worst-case power surge, a formula for keeping people safe, a formula for making the foundation strong, and a formula for making sure the gas stays put. It's how you turn a complex idea into a powerful, physical reality.
It's pretty incredible, isn't it? This amazing fusion of different kinds of engineering is humming away, hidden in our cities, keeping our modern lives running. It's a silent giant. Which really leaves you with one big question. If this is the amazing engineering that powers our world today, what kind of genius are we going to need to power tomorrow?